All right. Well, morning everyone, and welcome to the next installment of the JKMRC Friday morning seminar series that take place here at the Indurpili Lecture Theatre and online. My name is Katerina, and myself and Karina are co-chairs of organizing the seminar series this year, and we take turns introducing the speakers. So before we start, on behalf of the University of Queensland and the Sustainable Minerals Institute, we'd like to respectfully acknowledge all traditional owners and their custodianship of the lands on which we all meet today. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country. We recognize their valuable contributions to Australian and global society. Our speaker today is Dr. Sandra Rodrigues, a research fellow at the School of Earth and Environmental Sciences here at UQ. She is a geologist by education and specializes in organic petrology, organic, not inorganic petrology, having worked on projects related with coal and petroleum systems. She applies organic petrology to evaluate the rank or maturation and composition of coal samples and shales from different Australian basins as well as the overseas. Additionally, Sandra has been working on the characterization of the mineral matter using microscale techniques such as optical microscopy, SEM, EDS, and ChemScan, as well as scanner technologies such as HiLogger and CoreScan and iTrax Core Scanner at University of New South Wales. Recently, Sandra has been working on the hyperspectral characterization of coal, and that's how we met several years ago, and I've pestered her incessantly ever since to present, and she's going to tell us all about the black over black work right now. Thank you, Sandra.
Thank you, Katerina. Hi, everyone. Thanks you to be here in this cold morning. I hope you enjoy my presentation. Today, I'm going to talk about the upper spectral characteristics of coal samples. This is just a short presentation that was based on the ACAR project that we finalized last year, and where we built the spectral libraries for coal samples with different ranks. So the team was composed by myself, Lionel, he's a spectral geologist working at CoreScan, and John, that's sitting here in the crowd. The funds for this project came from the Australian Coal Industry Research Program, ACAR, and we acknowledge the support of the coal mine companies that supply the samples for this study. Hi, Gary. I'm Mike. Yeah, so how does it click on the screen? Thank you. So before starting talking about the spectral features of coal, I will talk a little bit about the infrared spectroscopy. We'll introduce coal as a geological material. The scanning systems that we use in this study, which core samples, and the infrared spectrum of the coal, how the spectrum varies as the coal evolves, and how we can map the geological features of the coal using high-resolution upper spectral scanners. If I'm going too fast, just please make me slow down. Or if you have any questions during the presentation, feel free to interrupt as well. So just a little bit of theory on the technique. So basically, you are using infrared spectroscopy. This technique corresponds to the measurement of the interaction of the infrared radiation with matter, which can emit, reflect, or absorb light. This can be measured by a detector or spectrometer, which produce an infrared spectrum. The spectrum corresponds to a portion of the electromagnetic spectrum that you can see here on the top. And the portion that is important to us is this one. and it comprised of the visible near infrared, the short wave infrared, the middle wave infrared, and the long wave infrared that have different wavelength intervals. In the same way, hyperspectral imaging collects information across the electromagnetic spectrum. The spectrum is divided into several bands, as we can see in this figure. And in the case of the hyperspectral system, more than 100 bands can be collected over a continuous spectral range, and it can be used in remote sensing or at laboratory scale. So before we pass to the spectrum of the coal sound, let's talk a little bit about coal. Coal is a geological material composed over 50% of organic matter, particularly remains it is composed from remains that come from higher plants, such trees and bushes. And that's why the big coal fields are from Carboniferous age and above, when the plants started to dominate the terrestrial environments. But besides organic matter, coal also has minerals, either dispersed in the coal matrix or filling fractures and cliffs. So coal is an amorphous material. It doesn't have any crystalline structure, but in hand sample, it has a texture that we call banding. And to this different banding, we call lithotype. So when we look at this image on the top right, we can see that there are bands that shine more than others. To the shiner ones, like this one here, we call it bright bands. And to the dull ones, like this one just immediately below, we call it dull bands. We can see also some lenses, the Fissam lenses. Maybe you cannot see very well in the screen, but they are so small lenses that occur dispersed in the organic matrix. So the bending in the coal, it's controlled by the polar environment at the time of deposition. Therefore, coal can be used for paleoenvironmental studies. So in the same way that we have minerals in hard rocks, when we look at the coal sample under the microscope, we can see different organic components that we call mesols. These mesols have different optical and chemical compositions that change throughout the diagenesis of the coal through a process that we call qualification. After burial, the organic matter becomes more aromatic and carbon-rich, and if the temperature and pressure conditions are right, we have the formation of graphite. So we're going to have 100% carbon. So let's step back a little bit here. And when we look at this optical image that we have here in the bottom right, we can see different gray colors there. So let's just ignore this very dark material, which is our resin that we use to prepare the sample. And let's look at the gray tones. So we have this intermediate gray tone that correspond to the mesoral groups of the vitrinite. And then we have these lighter ones in gray and white, which corresponds to the mesoral groups of the mesols of the inertinite group. And we have these very dark ones, tiny ones dispersed in the vitrinite, which correspond to the liptinite mesols. I will talk a little bit about these names throughout the presentation, and just to know that inside each group we have other individual mesols, and I will not talk about them specifically during the presentation, but we have three main groups of mesols that compose the coal. So on this slide, we have the main coal rank parameters. The term rank expresses how much the coal evolved in the sedimentary basin in function of temperature, pressure, and time. These parameters will be important further on during the presentation, as we will plot them against some spectral features that we can calculate from the coal spectrum. So as the coal evolves after burial, so its chemical and petrographic characteristics. So we have here the vitrinite reflectance, and the vitrinite reflectance increases with rank, the values that we can obtain. Chemical parameters such as moisture and volatile matter, they will decrease as the rank increases, while carbon will increases during qualification. One thing that we need to know is about moisture. This is only like a good rank parameter for lower rank samples. And it's going to be also an important aspect when we start looking at the coal spectrum, and we will see that. So one important thing to retain for the rest of the presentation is that coal changes as it evolves in the sedimentary basin, and this evolution can be quantified and by determining the rank of the coal, which can be done by optical and chemical methods. So how can we see the evolution of the coal in the spectrum? So that's why we are here today, and I will try to show you that. Taking all of this in consideration, we select our samples in order to cover a good range of coal ranks from subbituminous coal to low volatile bituminous coal. So we have around 14 samples in this range of coals. They all came from Australian basins, from the Galilean and the Bowen Basin, which are Permian Basin, and also from the Surat Basin, which is from Jurassic ages. So this table shows the specification of the instruments that we use in this study. We use two different ones that cover a wide range of the infrared spectrum, from the visible near infrared to the long wave infrared or thermal infrared. So it goes from 450 nanometers to almost 50,000 nanometers. The spectral range of the different systems overlap each other, and you can see that in this line. However, we select a wave range for each instrument as is specified in this line here. I will not enter in detail of the specifications for the instruments, but we can discuss later if needed. So we use two automatic scanners, the core scan and the high logger. The core scan was used for the visible near infrared and the shortwave infrared regions, while the high logger was used for the long wave infrared or TIR. For the handheld system, which is this small instrument here, we use it to cover the middle infrared. Here we have Lionel really happy scanning our samples at CSIRO in Perth. It was quite fun actually to be there and do that. Anyway, the use of the core scan and high logger are well established for mineral identification. These systems have spectral libraries that allow for the sample points to be matched against a reference spectra. But what happens when you are scanning coal? So when we started the ACART project, there were no spectral libraries available for coal, either in the USGS website or similar websites. People were scanning coal samples, but didn't have anything to match against. So when we have a mineralogical profile from the high logger, for instance, the organic matter would appear as a spectral. So with the ACART project, we create a reference spectral library for coal with different ranks. And we are hoping that soon we can upload this library into the National Virtual Coal Library, and then it can be accessed freely to everyone that wants to use it. So currently the library is sitting with us and me and Lionel, and if you need it and you want to upload to your systems, we just need to ask us. So we also scanned different surfaces of the same sample. That is, we scanned the outer core and the slabbed surface. We also crushed a quarter of the core to produce a compressed powder pellet. This pellet doesn't have any binders; it's just cold particles, just pure cold. So with the high logger system, what we did was 3 longitudinal transepts, both in the outer core and in the slab surface, and we took 1 to 2 points in the compressed powder pellet. The core scan, it's a high resolution system, and actually do a swab through all the surface. So we actually can map a high resolution, our samples, and we did that for the outer core, the slab surface, and also for the compressed pellet, if I'm not mistaken. So with the handheld system, what we did was taking sample points every 2 centimeters, more or less, in the slab surface, and 1 point in the compressed pellet. We were not able to get measurements with the handheld system in the outer core because of the curved surface of the sample. And we did this to see if there were some difference in the spectrum when doing to the different shapes. And if you look, what we found was that the spectral features are the same for the different sample preparations. However, if you look, for instance, the green and blue lights, which correspond to the pellets, we can see that the absorption features are more enhanced in this type of preparation than in the slab surface and outer core. And that happens to all the samples and in all the systems. So I will not enter in more detail around that, but through all the presentation, with the spectrum that we're going to see, they all come from the compressed pellets because we can see better the absorption bands there. So let's look at some spectra of the coal. We can see there is a lot of information in this image that needs to be identified, interpreted, and see how those features vary with rank. We are just going through the main absorption bands in this presentation. They are all described in detail in the CARP report, and we are also preparing a manuscript which is almost ready to be submitted. So first of all, it's important to know that the absorption bands in the middle infrared region, which correspond to these lines in blue, correspond to the fundamental molecular vibrations of the organic matter. So the spectral features in the middle infrared region are stronger. In the shortwave infrared, here in the green colors, correspond to the overtones and combination of the features that we can see in the middle infrared, while the long wave infrared OTRR, here in red and yellow, correspond to deformations or rotations. In this figure, I'm going to present only 3 different samples, because if I put all the samples, all the spectrums here, we cannot see anything when you have 14 or 18 different samples. So I'm going to present just 3 samples through all this presentation, which correspond to the lowest rank sample that we have, the subbituminous coal. And then we have an intermediate sample of our data set, which is a high volatile bituminous coal, and the highest rank sample, which correspond to the low volatile bituminous coal. So let's start looking at the spectrum, and let's start looking at bands that correspond to the structural water in the coal. We can see that these bands appear in both in the swirl and in the middle infrared, and that these bands, as the ranking prices tend to become smaller, like we can see one here, and then it's almost not existent as we increase in rank. It's really hard to see. And in the case of the band in the middle infrared, here at 2940, it becomes, the depth of this band becomes shallower as we increase in rank. So when we use the spectral parameters such the area of the bands or the spectral reflectance, and relate that to the moisture content of the coal, which was obtained by chemical methods, we can see there is a relationship, but this relationship is only good for the lower rank samples. And if you guys remember that when I said about moisture content is a rank parameter only good for the low rank samples. And the spectral parameters that you choose here also express that. So at higher rank samples, we cannot differentiate between our samples anymore. So other important components in the coal are the aliphatic and aromatic compounds. It is expected that the aliphatic decrease and the aromatic components increase during coal evolution. So let's see how they occur in the spectrum and how they vary. We can see that aliphatic bands appear in the swirl. So we have two small aliphatic bands in the around 2,300 nanometers to 23 to 50 nanometers. And this band gonna also becomes smaller as the rank increases because we are releasing all the aliphatic. And pay attention because this is the lowest rank sample, and this band gonna be important further on for our spectral mapping, and we will see that later. We can see also bands, aromatic bands and aliphatic bands appear in the middle infrared. We have a few there, so let's look at this area a little bit in more detail. So in the case of the subbituminous coal, we can see that the aromatic band is really small, and the aliphatic bands are quite thick and broad. When we go to our intermediate sample, the aromatic band is now quite visible, and our aliphatic is still broad, and one of the bands starts to split. And at the higher rank sample, we still have the growth of the aromatic band, and our aliphatic bands tend to become smaller. So if we do a ratio of the aromatic band over the combined aliphatic bands and plot that against the rank parameters, in this case we have the vitrinite reflectance, we can see that there is a good correlation here. And the same happens when we plot the carbon content or the volatile matter, also with rank parameters for coal. So what this can indicate is this spectral ratio that we have. It can be used as a rank indicator when we are using upper spectral systems. What we can see also from this graph is that we have a sample that gets out of this trend, this one here, and this particular sample is reaching a measure called inertinite, which is the whiter or the lighter gray that we saw in the image, and it is almost composed by aromatic compounds, and that's why it gets out of the trend there. So this indicates also that this region of the spectrum can also be sensitive to coal composition. So we have other aromatic and aliphatic bands in the middle infrared, but these bands present more variability between the samples, and the correlation with optical and chemical parameters was not as good as the spectral ratio that I showed previously. So, but we can still see the development of this aromatic band here, and the increase in depth of this aromatic at 6,000, and we also have an increase of the aliphatic band at 6,200. In the case of the long wave infrared region, it was actually hard to get some information about the coal itself. We have a lot of interference of the mineral matter in this region, but we have two bands here that may correspond to aromatic. The high logger, we were not very successful with the high logger. Maybe it's a question of the resolution of the equipment, and maybe we need to adjust a little bit. We actually didn't do that experiment of setting up the scanners to scan the coal. So we didn't change the settings. So we now know our spectrum, the position of the bands, what they mean, and how they evolve during qualification. Do you have any questions about the bands before I move on to spectral mapping? No? All good? Yes.
Just on moisture, because there's maybe mineral processing people, is that bound or free moisture?
Bound, yes, not free moisture. I think we have experience with free moisture of water in the samples that we are using in the plot logic. And we can see it in a different, what was the band there? 1,400, Gary?
Yes, so 1,400 and 1,800. There was
Yeah.
absorption.
Yes. So that was because the samples were a little bit wet, and we could see that in the spectrum. But in the case of the band at 1910 is actually the moisture, the bond moisture. Yes. So we know also that we have spectral parameters that correlate well with optical and chemical as well. And maybe we can use some spectral parameters to actually estimate the rank. So what else can we do? We can also create spectral maps with the coal samples. So with the core scan, which is a very high resolution scanner, it was possible to create a map showing the lithotype variation within the organic matter. So this table here shows the diagnostic features of the lithotypes. The diagnostic features use it to map the lithotypes. So for the aliphatic fraction, we use the band 2310. I don't know if you guys remember it. This tiny band here that we can see, and then decreases with rank. For the bright bands, for the bright and dual bands, we used a threshold for the albedo in the interval between 448 nanometers and 740 nanometers. So if the average of the spectral reflectance in this interval is less than 0.06, then it corresponds to our bright bands. But if it's higher than that value, it would correspond to the dull bands. For the Fusane lenses, we use a spectral gradient between 2,400 and 1,200 nanometers. So let's see if this actually works. Yes, it worked. most of this part of the spectral mapping was actually done by Lionel, and it was quite amazing to see that all of our background of actually figure out what meaning all those squiggly lines that we can see and actually build up the mapping was quite amazing to see it happen. So anyway, so we have here 2 samples only. So I'm going to present an example of a subbituminous coal and a high volatile bituminous coal. And for both samples, we have like 3 profiles here. One is a high resolution photo. The other one is a mineral matter class map. And we have the lithotype class map that was built based on the diagnostic features that we that I presented in the previous slide. So let's look at the lithotype class map of the bituminous coal. It shows that this sample is a aliphatic rich coal, which is actually quite true because this particular sample comes from the Surate Basin, and it has a high liptinite content above 30%. Liptinite is the mesurable group that is richer in aliphatic compounds, and those aliphatic compounds appear dispersed in the coal matrix, and that's why the spectral characteristics appear like mapping this way. It's not like a band, it's actually dispersing through all the matrix. In the case of the lithotype class map for the high volatile coal, bituminous coal, we have banding between these yellow bands, which are the bright bands, and the green bands, which are the dull bands. We can see also some fusane dispersed in the matrix. And when we look, I hope you guys can see it. When we look at the photograph, we can see that we have the fusane here. Okay, we also have the bright bands there. We can see in the photograph, in the map in the yellow color. We have some problems during mapping because coal breaks quite easily. And in the case of the bright bands, they are quite fragile. So we kind of have a lot of holes there that bring us a lot of problems. Another issue that we have during the scanning and during the characterization of the coal was this marks from the cutting when we slab the core, and they needed to be masked. That's why it appears here in black, because they are very high reflective. But even so, we cannot get rid of all the saw marks there. So that was an issue that we kind of need to solve through the project. Even so, we are able to map the coal, and we actually have good correspondence to what we see in the hand sample. Regarding the mineral maps, we can see here calcite that fills the fractures there, and you can see some clays. I don't know how real this is because it's gonna map, I think, inside these broken fractures, but it should be the mineral matter infilling the clit system. So I think I'm almost done. So in summary, although coal is a very dark material presenting some challenge during scanning, such weak absorption features, it was still possible to acquire spectral data without changing the settings of the commercial available scanners to characterize the coal in a wide region of the infrared spectrum. We still need to improve in the long wave infrared when we are using the high logger. The spectral features of the coal are more prominent in the middle infrared, as this region holds the fundamental molecular vibrations. Spectral features have correlations with chemical and optical parameters that express the rank of the coal. So there is a possibility that hyperspectral scanners can be used as a approximate tool for coal rank. And never forget, coal is a rock that evolves and acquires other properties after burial with increasing temperature, pressure, and time. Therefore, when we use these scanning technologies, it is fundamental to have that in consideration, as the spectrum of the coal also reflects those transformations. Thank you. I don't know if you have any questions more.
Thank you, Sandra. That was fascinating. It is black.
Only you can think that is this. I don't know. I found really challenging to make this presentation quite exciting because it's just quick with lines all the time. It's kind of hard. So I hope you guys are not too bored with that.
Not at all. Do we have any questions in the audience? We do. Fantastic. Several.
Yeah.
Oh.
Hi, thank you for your presentation. It was very clear. My question is what's next? Like, what kind of techniques would you like to use, maybe to improve the results that you got? If you have any things about that, or I don't know, any other applications that you see this?
So I would like to improve a little bit, if possible, to long wave infrared. I think we didn't get very good results there, and I would like to see if we can increase the spatial resolution of the scanner and try to improve that area a little bit to characterize the organic matter. Another thing that I would like to do, that I forgot actually to mention, is to include in our library the lignites and the anthracites as well. We didn't do that. We were not able to access that during the project that we did. Another thing that I would like to do was to include heat affected coal to see how that changes. So when you have a coal seam and you have igneous intrusions that come to the seam and affect the coal thermally, so it alters that coal, and how can we see that in the spectrum as well? I know that CoreScan is now trying to build one single machine where you can have all the spectrum from the visible near infrared to the long wave infrared in one single system. So let's see if that's actually gonna happen. And then you can scan all the core and have a full range there. I don't know if this answer to your question or not.
Sandra, thank you for your presentation. I have to admit, before presentation, I don't know a lot about coal, but after this one, I definitely know. I don't know, not a lot. Huge things. Anyway, so my understanding is that what is the area of when you run the analysis of hyperspectral? What is that surface that you analyze and produce that line?
So
is it a spot or a bigger area?
So in the case of a CoreScan, it actually maps the whole sample. You kind of have like a overlap of the reading of the surface. But in the case of the high logger, it's a spot analysis, but you kind of have a profile through all the core. So yeah,
My
so
question is
The spot size on CoreScan, so it's so in CoreScan, I think it's 0.3 millimeters grid, across the swath, and then the actual size is 10 microns, I think, the spot size,
And that one,
4 nanometers?
4 nanometers. Okay,
that
so
one
it's that one.
spectral line is combination of all those.
Oh,
It's just-
so yeah, yes.
The question is, in the earlier at the presentation, you said you analyzed the surface of the core,
Mm-hmm.
and then for some fraction you take and you powderize, make a tablet and analyze that.
Mm-hmm.
So my question is, how did you merge those? You have one spot. Basically, in the second one, you destroy that information of location,
Yes.
and you like blend everything, which is what for XRF you would do that to have a true representation. What is it?
Mm-hmm. So in the case, yes, so when you do all this, we're gonna have like thousands of spectrum in one sample, right?
Yeah.
What we did is see how good are those spectrums and then average that spectrum to one sample. Does it make sense?
Yeah.
Yeah, otherwise it would be impossible to deal with individual spectrums for the samples.
Yeah.
So all the spectrums that I presented here, this is average
All.
of all,
And
yes, for a given sample. I don't know if that makes
And
sense.
any correlation with those cases when you powderize everything?
Yes, so there are. So here in this image, for instance, we have 2 different samples at different wavelengths, right? And we can see that the spectral features are exactly the same, okay? And we have basically the same trends when we plot against chemical and optical parameters. But in terms of visualization, it's the pellets, the compressed powder, right? That shows the best features for our eyes to see, okay? It's just a matter of, in terms of visualization, the pellets are better, which are the green and blue colors. You see they are deeper,
Yeah.
right? And as we increase in rank, since the spectral features becomes also weaker, it's the pellets that gives you a better visualization of the spectral features.
I think also on that, it's why you use some spectral ratios a lot of times to try and normalize for that absolute value. When you early days of FTIR, you crushed everything up and made KPR pellets.
Yeah.
And then you had a piece of paper and you sat there on a light table and you just measured ratios because you had no normalization.
Yeah.
And so I guess in this, what happens is the powdered pellet could start to become the standard, if you will, and then you use that to apply to your spectral deconvolutions along the way.
We also have a couple of questions online as well.
Thank you very much for the presentation. It was very nice. My question, did you look for the calorific values of the measurements? And did you find any correlation between the qualification calorific value and the data you show here?
Calorific value?
Yeah.
We didn't have actually data for calorific value when we did proximate and ultimate analysis, but not the analysis for calorific value.
Okay.
Okay, sorry.
But they all follow.
But they all fall, yeah.
Yeah,
They
they
follow the
follow.
rank.
So you could set up basically calorific value is a function not only of the carbon content, but the ash or the mineral matter. And so you could start to take that data and come up with an estimation.
Yeah, because this might going to give an estimation of the overall calorific value average and volatile matter you have in your core samples, but you have also pulverized data that can give a specific data analysis of the calorific value for each measured group. Can give another, because you say that you are building a library of all this data, right?
it can give another indication. Yeah.
Thanks, Sandra. I was just thinking with that, when you're doing the big scans of the cores, and you have the saw blades, and you say that it starts cracking in it, that affects resolution, I guess, of the sample. So would it be interesting maybe to subsample that and embed it and grind it and get really high resolution scans so you can like actually see nicely what's happening? Or is it we're not concerned with a really detailed scan of small subsamples?
So one of the things we did at the very beginning, a few years ago, core scan, was take our polished pellets.
Oh, yeah.
Yeah, so initially we tried to take polished pellets where we had an absolute glass mirror on the top, and the reflectivity was so high that it was tough to follow. So I do understand your point, because that goes to kind of using hyperspectral with the billet scale, you know, or the thin section scale, which is the schema that.
I wonder if you grind it so you take off the glare and just have it in a really tight in situ.
Yeah, you could, but it gets hard. I mean, you grind it,
Yeah.
right? And the question would be to develop a grinding technique where you ground it, but you didn't polish it. Because once you start to polish, then the sheen comes up on everything. And I mean, we could see, like, we were actually still quite impressed with the way it behaved on the pellets, but not, you know, like you'd really want to come in and actually put it on a microscope. You'd have to change your system technique. So it would be good to do hyperspectral.
I have a couple of questions online. Julie Pierce is asking, would it be possible to use such technique where coal is in layers or of sandstone, for example, or in shed?
Like when you see in the sim? Yeah, of course. Yeah, of course.
Easy peasy.
Easy.
And Regina Baumgartner is asking, just curious whether it's possible to combine data from hyperspectral scanning and from PUS, or do you have to level the data? Also curious if you've
Can you
looked,
repeat the question?
is it possible to combine data from hyperspectral scanning and from the pellets, or do you have to level the data?
It's possible to combine.
It's possible to combine. And if you look, have you looked at hyperspectral proxies for things like ash content? I know some of this work has been done in the past, but whether it was part of this project.
Not part of this project, but probably in the project that I'm doing now.
Current project.
Yeah.
Alicia Caruso is asking, how did you determine the presence of mineral matter? And if your albedo scaler needed to have pixels with mineral matter removed, did you manually mask them out?
Yes, so we masked the mineral matter out, and that I think it was in the table for the diagnostic features. So we masked all the mineral matter out. So when we scan the core, the mineral matter is automatically recognized. It's in the system of the scanners. So you have your mineral matter there, and that just masks the areas where that mineral matter was identified. So it's also quite a simple process.
Did you find any misclassification with other minerals when using your scalars, depending on feature weight?
I don't know. I don't know how to answer that question because it was done by Lionel, but I don't think we had any problems. The minerals that appear in the coal samples were the typical minerals that you expect finding coal, but we didn't do any like XRD analysis to prove that those minerals were exactly the ones that appear in the upper spectral, or do any SEM analysis on the mineral matter, because we were just focused on the organic components of the coal.
Fantastic. I guess it depends on the reference library that you use. And have to trust the process. Couple more questions. Is it possible to identify and differentiate ore samples with coal, carbonates, and graphite in low proportions?
Can you repeat the question again?
Is it possible to identify and differentiate ore samples with coal, carbonates, and graphite in low proportions?
Gold, carbonates,
Yeah.
and graphite?
In low proportions.
I would say yes. So the carbonate is a mineral, so it should have the usual spectral characteristics of the carbonate. Regarding graphite, I actually don't know how we would see the spectrum of the graphite because it's such a high. I think we had that discussion, right, Mike? Graphite is just pure carbon. So when we look at the coal, and as we increase in rank, we're going to have the absorption feature is going to be weaker and weaker. So the graphite would be like the extreme of that organic, of the evolution of that organic matter. So I don't know if we're going to see just a straight line. So it's a straight line identifying graphite. I don't know how to answer that question because we didn't do actually any scanning of the graphite. So, and I don't know what FTIR, which would be another equivalent technique, would give for the graphite as well. Do you have any idea?
What we get closest to graphite is, the closest thing to graphite we have scanned is the carbon electrodes used for limited smelting. So they are not quite graphite, but they're reasonably close. So pure carbon, and yes, it's absolutely featureless. It's just slightly rising spectrum. So yeah, very difficult to distinguish between the shade and the graphite.
And that's in the SWIR or?
In the linear sphere region.
So Mike and Gary, they work at Blood Logic, so they will tell us about the scanners.
We'll do this later. One more question. Is it possible to identify liquid substance such as oil or maceral related to it, such as into clay minerals?
Ooh, that is an awesome question. So yes.
This is from Rana Ismailpour.
Right. So the answer to oil is yes. So people are using the SWIR region to detect other carbons. Yes. For excidenite in clays, in the case of the coal, I don't know how if that is possible or not, because you're going to have a lot of interference of the rest of the organic matter in coal. But for other carbons, for oil in shales, yes, it's possible to identify. I think Lionel has been doing that anyway.
We have to stay tuned to some exciting publications or presentations. Sounds great. Do we have any more questions in the audience? If we're out of questions online as well. People are saying great presentation.
Thank you.
Lots of praise. All right, I guess on this note, we can also wrap up. So next week we have JKMRC alumni Dr. Stephen Rayward presenting on flow sheet based simulation system. Thank you, Sandra. We will see everyone next week. Cheers.